So greetings and welcome to today's educational program. DOE Demystified. If a fourth grader can do it, so can you, by Jd Marhevko. This is your moderator, Doug Wood, with the ASQ's Quality Management Division. Now, today we have the distinct pleasure of having Jd Marhevko. She's going to talk about design of experiments and how to do it easily. Please join me in welcoming her to this talk. Now, in case you don't know about JD, she's a VP of Quality for the Electronics and ADAS division of the ZF Group. She has approximately 35 years of progressive executive leadership experience in multiple industries, including automotive, military, aerospace, food, medical devices. She was inducted into the USA's Women in Manufacturing Hall of Fame and holds several honors, including an ASQ Shanin Medal and an ASQ Fellowship. She has helped to transform several organizations from bankruptcy to best in class. In one business, 4 sites were honored by the Association of Manufacturing Excellence, getting an AME Excellence Award as best in class in industry. JD has co-authored several books and articles on lean and quality systems. She's an adjunct professor for the University of Michigan Nexus and serves on the board of directors for an aluminum casting firm. She holds a BSc and an MSA. So without further ado, it is my pleasure to introduce Jd Marhevko. JD, take it away.
Thank you, Doug. Hey, I saw Steve Shulka out there. Hey, Steve, thank you so much for joining. I see India, Mumbai. I see Australia. Oh my gosh, how many wonderful people out here. Thank you so much for joining. The slides are available as a PDF at the end of the session, so Doug will take care of that. And we'll move along. I think we will. So what we're going to do, we're going to walk through the overview of the basics of design of experiments, DOE. If you don't have something handy, I'd like you to have a piece of paper and pencil handy. We're going to do a little bit of work, and we're going to break down the basic steps of conducting a 2-level, 3-variable design of experiments. Talk about how it works in concept. So, like I said, please have a calculator, paper handy, because we will be interactive. In this little model that you see right now before you, this is what we call a 2x2. This is the simplest kind of design of experiments it could be. Let's say I wanted to know if shoe size, the size of my foot or the size of my shoe, was dependent on how tall I was and whether or not I was male or female. So my male or femaleness, my gender, would be one variable, and the other variable would be if I was short or tall. And we fill out this little table here, and I'm looking to see if, if I have a short man versus one who's tall, or a guy, from a gender perspective, if he's short or tall, and a female, and whether she's short or tall. And you see that A times B on the right-hand side, and those are what we call the interactions. If I have a male, I set one as a negative and one as a positive. It can go around the other way as long as I'm consistent. But we use this coding of plus ones, minus ones, so we can see these interactions. And we'll show you how those work, because that's what allows us to do the DOE analysis, these positive and negative ones. What we're going to be doing is a 3x2. We're going to be doing 3 variables at 2 levels, a high level and a low level. So example, you can see in that first variable column, column A, I've got 4 times where it's going to be set at the low level and 4 times at the high level. The second variable B is going to be, again, 4 times at the low, 4 times at the high, but now you see a pattern: too low, too high, too low, too high. In that third column over there in variable C, again, you're seeing set 4 times at the low and 4 times at the high, but now you're seeing alternating, minus, plus, minus, plus. And the formula of how many experiments we need is the levels, how many levels we have, and in this case we have 2 levels, a low and a high, to how many to the power of how many variables we have. So this is 2 cubed. So 2 times 2 times 2. 2 times 2 is 4, times 2 again is 8. Means I need 8 experiments for this design of experiments set of the setup that I'm going to try and run. And we're actually going to do a real one that we did in a real life shop environment. When we do a design of experiments, it's a guideline. It just helps you set up how to plan your experiments. Which settings are you going to have it high and low? How many times are you going to do it? And it allows you to optimize or improve how you run your process. And it lets you see what your key input variables might be. If I have a process, I could have hundreds of variables going in: speed, temperature, different kinds of materials, whether I'm using aluminum or steel or something. It could be a density of a material. Could be a humidity setting. There could be all kinds of inputs that affect my output, what I'm looking on the right-hand side. That's called the response. How did my process respond to those various variables? I could be looking at my pass-fail rates. I could be looking at a desired dimension. I could be looking at a desired attribute. Does it have holes, big holes, small holes? Is it scratched, not scratched? I could be looking at efficiency of my process. Lots of different outputs I could look at. When we do a design of experiments, it's really powerful because it helps us save money. That's what it does. And it really allows us to control our approach so that we can really get that optimum process figured out. Some of the cons of an experiment is it does require some process and knowledge, and you need to use the right software, whether you're using Excel, which is totally fine, Minitab, SQL, JQ, there's all kinds of software out there that allow you to do design of experiments, and they all work. I just grew up on Minitab, so that's the one I know, but I practically do most of mine in Excel because I only do the smaller versions, either a 2x2 or a 2x3. I find those to be easier, and then I end up iterating my different variables, and it's a faster way sometimes than approach. It just depends on the complexity of what you're dealing with. So when you're doing a design of experiments, I can't stress enough, the measurement system has to be looked at first. That is always the first step of any MSA, of any DOE. If you decide you want to do a design of experiments for whatever reason, you have to do your measurement system analysis first, especially even if you're doing an attribute. If you're looking at the visualness of a product as your result, and you want to see, is it shiny enough? Is it smooth enough? Does it look good? You still have to have that form of measurement system analysis completed for the attribute and or for the variable. Because if the data isn't accurate, the results aren't going to have meaning. So here's your general approach. You conduct the MSA, the measurement system analysis, and then you evaluate, even if you need to do a design of experiments. Maybe you don't. I call the DOE heavy artillery. Most problems can be solved without a DOE. But some can't. Some get a little bit more hairy. A lot of chemistry, physics, things that you're going to be doing, a lot of things that are interacting with each other really lend itself well to a DOE. You want to identify your variables, and you'll see the term variables and factors used interchangeably. And then your levels. Usually you'll have 2 or 3 levels. Sometimes if you get really into this, you can have 4 levels. Those are pretty painful, but it can be done. And then you lay out that experiment grid like we showed you, and I'll show you how to lay out a grid. And then you understand the workload. So I'm going to do 8 experiments. How long is that going to take? Is it an hour per experiment, a day? How long does that take? How many people do I need to run those? And maybe I have to get extra permission because I need extra materials or extra time, or I need to cut into the production line. Then you actually execute the experiments and look at the results. And that's what we're going to do. But the first thing is, let's talk for a few moments on measurement system analysis and why this is so critical. When we are doing a measurement system analysis, you can assess the effectiveness of your measurement system, the accuracy of it, by calibration. And then the actual precision of it gets assessed by your gauge R&R. Your variables, gauge R&R, is measurement error. And if you're using attribute agreement analysis, or on the attribute side, you're using some form of statistical agreement analysis. So either way, you want to assess how good you are and consistent you are getting the right kind of reading. And then you also have to make sure you have good resolution. How well can you read your instrumentation? So in this case, in that clock on the right-hand side, it's 10, 10, and 35 seconds. My resolution, I can read it to the nearest second. So is it 35 seconds, 34, 36? I have some ability to discriminate within that second. If I pull that second hand off, it's now 10:10. But is it really 10:10 or is it 10:09 or 10:11? Now my measurement's going to wiggle a little bit. I have to infer. And if I remove that minute hand, now it's 10 something. Is it 9 o'clock, 10 o'clock, 11 o'clock? And again, now I'm inferring across a much wider range of measurement. So you need all three of these things to know that your measurement system is working for you like you want it to. There are more aspects to a measurement system. These aren't the only three. These are the key three that I look at. And you need all three of those to get a good result, or to guarantee that what you're looking at is good. When we do when we do a design of experiments, we're not taking lots and lots of readings. If I do 8 experiments and I have 8 readings and that's it, if any one of those is off in the littlest bit, my whole experiment could be giving me the wrong set of directions on what to do next. So it's really, really critical that your MSA is accurate and working for you first. When we have a measurement system analysis, you could either have what's called an alpha risk, which means, oh, darn, I rejected a good part. That's how I remember alpha. Oh, darn, I just threw away something good. Customer is not negatively affected, but I'm losing money as the producer. Now, if it was a beta risk, that means I could pass a bad item. Boy, that's bad. Beta's bad. That means I've accepted a bad part and I didn't know it. Again, in a design of experiments, you're only taking typically a few data points. So those readings are critical to the effectiveness of the decisions you're going to be making. And I kind of show it this way. In this case, I have a process here. I'm going to put on my laser pointer here. And I've got my process distribution that is consuming the full specification. So if my process, my specification is -10 to +10, and my process is also running from -10 to +10 in its distribution, and if I have a gauge error of 10%, so if my gauge reads a 10, and this is whether a human is reading the gauge or if it's an automated gauging system, it doesn't matter. If it reads a 10, it's going to accept that part. It's going to say, it's good. However, if my process is creating product up here in this 10 range, which this one is, every time I get a reading of 10, 1/3 of the time, it might not really be a 10. It might really be an 11. But my process has accepted it. So if I have a process this fat when I start out, then I'm at risk 1/3 of the time whenever I get a dimension at the spec side of actually having a beta error. If my gauge reads an 11, either my human or my automatic gauging system, they're going to throw it out, all right? Like they should. However, again, if my process has created a part on that side of the spec, 1/3 of the time, it might be a good part. And here I've made an alpha error where I've possibly thrown away a good part or I have to rework it. So this is a risk we have when we have process. And typically you want to see what the variation of your process is doing. We need to remember that our process only covers 99.7% of our stuff from tail to tail. And because I have 6 sigmas, or I have 6 standard deviations of product underneath from tail to tail, only 99.7 of my stuff is underneath the bellbrella. And I call that bell umbrella, the bellbrella. And I'm going to have 3 parts per 1,000 out of spec or out of the tails on this process. With that said, I'm going to be making alpha and beta errors with a process like that if I have a 10% error gauge, which I'm allowed to have. Industry standard allows you to have 10% error in your gauging system. So when we're looking at our process, it's often important to see where your capability is at before you start. And this process is skinnier. I can fit 5 standard deviations, 5 sigmas between my average and my spec line. And this way, my process is not creating product at the specs at the spec line like the last one was. I mean, the last one, the bell was pretty fat, and I was creating tens. Now my process is not creating tens. I'm still going to have a 10% error gauge. Now, if I read a 6, my process can't create the error of accepting or rejecting. I don't have any alpha beta error risk going on over here. So typically, a design of experiments will help you reduce variation, help you get a skinnier process like this. But understanding the impact of your gauge error will help you with avoiding that alpha and beta error situation to begin with. But it's also why you need to do this MSA before you start your design of experiments to see if you have that risk. Moving on. So a design of experiments, we have variables and levels. So the variables are the different things that will affect the or impact the output that you're looking for. And these are just some common examples that you might see. And who you need to remember Alfredo Pareto. Alfredo Pareto was really cool. He said, look, 80% of the time, 80% of these of your variation is only going to be caused by 20% of your variables. 80% of your result is going to be caused by 20% of your variables. So I could create a design of experiments with 10 variables. I could do that. That's a lot of work. It's a lot of experiments. But in reality, I really only need to think about 2 or 3 of them. Now, if I'm wrong, I can do it again with another 2 or 3. So keep in mind, you don't have to throw in everything when you're doing a design of experiments. Pick what you think are the top 2 or 3 variables that are making the effect that you're looking for. Levels are typically at 2 or 3, usually a high and low effect setting. So if I wanted a low time of 60 seconds or a high time of 120 seconds, or it might be binary, it is or it isn't, no salt or high, has no salt, doesn't have salt. Or I could do a low, medium, high, 60, 90, 120, or maybe 3 types of metals. Those are the different ways we can do things. So we're going to go through a real problem. This was in a real production environment some time ago. And this was an assembly angle, theta, at assembly angles in there. And I have this spring, and I got these 2 pieces of wood, and they're hooked together by a little bolt. And this theta was important. This angle was pretty important to the production process. And the assembly angle was sometimes incorrect after installing that spring. And there was a lot of rework and component scrap going on. And the springs were being sprung. The springs are getting out of shape here. So the production teams were interviewed. So we actually went to the floor and asked the guys, okay, guys, what do you think's causing the angle to be wrong? And they said, well, some of these springs, they're too stiff, and some of them are super springy. And that springiness or stiffness factor, that's called a K factor in a spring. There's actually a feature that measures how springy a spring is. And then there were 2 different build fixtures. They had the 2 build fixtures were supposed to do exactly the same thing. Build fixture 1, build fixture 2. They were supposed to be exactly the same. But they said, well, maybe there's some kind of a difference between the 2 fixtures. We don't know. And then, of course, they said, well, it's second shift. They're making them wrong. It has to be the people. So they said, okay, there's a difference between first and second shift. And they did brainstorm some other ideas, but then they did some voting, and they said, all right, let's focus on these 3 things first. So now we need to set up the experiment. How can we figure out, is it the spring, the fixture, or the shift? And here's the grid. So I'm going to set up an experiment, 8 experiments here, because I have 2 levels. I've got either a stiff spring or a springy spring. I've got my 2 fixtures, the first one and the second one. And I've got my 2 shifts, the first one and the second one. And I've got 3 variables, the spring, the fixture, and the shift. So that means I need 8 experiments. And I can see these interactions going on over here, the A times B. So if it's a minus, so if I'm using a low spring and a low fixture, it's going to come out with a positive interaction. That's kind of how you look at it. So these plus or minuses here, these are going to be pretty important to us in a few minutes. But this is how we set up the experiment. And now the next thing I'm going to do is I'm going to lay in the actual product. So here I've got a low spring with the first fixture on the first shift. Here I have a low spring with the first shift fixture on the second shift, so on and so forth. I've got it. I have now designed my experiment with 3 variables at 2 levels. I know that sounds extremely complex, but that's all this is. So I've got 4 times where I'm using a low spring, 4 times where I'm using a high spring, 4 times where I'm using that first fixture, 4 times when I'm using the second fixture, 4 times when I'm running it on first shift, and 4 times when I'm running it on second shift. Now, officially, you want to shuffle these up. You don't want it to be biased. We call that being randomized, or you're shuffling them like a deck of cards. So instead of doing them in order, 1, 2, 3, 4, 5, 6, 7, 8, you shuffle them up. Depending on the process that you're doing, that may not be possible due to speed and time and efficiencies. But if you can shuffle them to avoid bias, you want to. So that's what we did. We had these 8 experiments that we set up. And here's what it looks like. So we've got the same experiment grid here on the left-hand side, and it's set up. And what I did was we ran the experiment 3 times. The first time we ran it, I ran the low spring with the first fixture with the first shift, and they got an 8.2 for that little bitty angle. That's a small angle, 8.2 degrees. And we did the 8 experiments, and these were the 8 different results for those 8 experiments. And we did the MSA first to make sure that the angle was accurate and the measurement system error was less than 10%. And then we did it again. We did a second replication. We replicated the same 8 experiments. We ran it again, and these were the results we got. And we did it a third time. Now, sometimes you're able to replicate your design of experiments. Sometimes you can't due to expense and time. Sometimes you're only going to get a chance to do it once. And in that case, your measurement system analysis is even more critical than ever before because you only got 8 readings. And if in this last one, if instead of 5.3, I got a 5.8 or a 4.8, if my values were a little, significantly off, it could really throw off the total results because this is only one data point out of 8 that's going into the calculations of whether or not these 3 variables are going to make a difference. So that MSA is really important up front. Now you can see on the far right-hand side, I've calculated the average of my 3 sets of readings. So 8.2 plus 8.2 plus 8.2 divided by 3 is 8.2. That's the only one I can do in my head. So that goes across, and I've got my average. Now what I want to do is I want to plug and chug. I want to be able to calculate what we call our main effects. So I'm going to flip back and forth for a second. So here you can see my average of my first trial was 8.2 of those 3 readings. And what we want to do is see which ones are low and high. So you can see where I color code it, and I keep the coloring coming over. So my first 4 were -1s, and my second 4 were positives. So you can see my 8 averages. And now my -1s where the spring was low and the spring was high. And then I have my fixture where that was the first fixture versus the second fixture, and first shift versus second shift. So here's how you calculate that main effect. What I do is I take the average of my A, the high responses. So I had 4 responses of this where it was high. I have my 5.9, my 5.7, my 5.4, my 5.3. I add them up and I divide by 4. That's averaging. So I've calculated the average of my high responses. Now I'm going to calculate the average, I think, come on, of my low responses. That's going to be the 4 up there. 8.2, 8.5, 7.9, 8.0. I ended up rounding this off to a single digit, 5.6, 8.2. Get your calculators out, folks, because you're going to be doing this in just a few moments, because you're going to be calculating the ones for the B's and the C's. But then the next thing you do is I've got my high average and my high and my low response averages. And now I subtract the 2. Now subtracting is first grade math. Averaging is third grade math, just so you all know. And then we subtract the 2 values. So the 5.6 minus the 8.2, and I get a negative 2.6. But in this case, we're going to take the absolute value. We don't care about the plus or minus. We're just looking for the distance, the difference, the effect of variable A. The total magnitude of effect of the spring is 2.6. That is how you calculate the effect. So what I have done is I have set up my experiment with 3 variables, 2 levels. I have calculated the main effect of variable A because I took those readings and I found the results that I got when the spring was high and the results that I got when the spring was low. I took the average of the first and I subtracted it from the average of the second and I got a distance. That's what I did. I've calculated the main effect of variable A. It sounds really complicated. It sounds really difficult, but all you did was averaging and subtraction. Wasn't that hard? Some of us can do this on our fingers and toes. We'll be going on to B and C in just a moment. And what we want to do is, these will be the main effects. So the effects are for the 3 big variables, A, B, and C. And we will plot those responses. If your response has an angle to it, if it's got any slope, it's got an effect. If it's flat, if the response is flat, there's no effect. So between the average of the high and the average of the low, if there's no difference, essentially, there's no effect. If there is a difference, there is an effect. It's yes or no. It's not that complicated. Later on, you get into what we call the interactions. Does the spring interact with the fixture? If it does interact, they're going to crisscross each other. They're going to crisscross like this. So the more they are perpendicular to each other, the more they affect each other. If they're parallel and they lay on top of one another and they're both taking the same path, they're not affecting each other. So in this first one, if the first feature, if the spring is not doing anything different than the fixture or than the shifts, if they're just running all in parallel to each other, they're not interacting. So as if you see something like this in this third picture, and it looks like they're on a runaway train and they're going to hit, you're making an assumption because you only did the experiment within this range from this point to that point. You're making an assumption that eventually it is going to interact. So you might need to do the experiment again to include the second, another pass on the other side, on the farther right-hand side, to see if it really carries on through. If it actually does interact, bam, you've got an interaction. So let's look at the effect of our spring. So we calculated that first one. It was 8.2. That was at the low value. And at the high value of the spring, it was 5.6. Oh, wow. I see an angle. Look at that. It's on an angle. There's a slope to this thing. That's telling me that there's going to be this, that the spring is having some kind of an effect on my angle. So now what I want you guys to do is, I've got the numbers in here. You can see them all. So what I want you to do is I want you to calculate the effect for B and the effect for C. And I'm going to talk you through this for about 2 or 3 minutes so that you can do your own math and plug and chug to see if you're as smart as a 4th grader. So for the main effect of variable B, so please do it along. Use your calculator, use your cell phone, paper and pencil, fingers and toes, whatever you need, to see if you can calculate the actual effect of these. So for variable B, I'm looking at it for the high responses. So I'm going to be looking at it when it's a high level, 7.9 and 8.0 plus 5.4 and 5.3. I'm going to add those 4 values together, divide it by 4, and that's going to give me my average of my high. And then I'm going to do the same thing on the low side where it's negative, the 8.2 plus the 8.5 plus the 5.9 plus the 5.7. Take those 4, average them up, divide by 4, and I've got those 2, and then we're going to subtract those 2 and take the difference and see how big of an effect is variable B having on our process. So that's the fixture. Is the fixture making a difference here, yes or no? Are we going to see as big of an angle on the fixture as we saw on the spring? Then, yeah, you got the right answer. Thank you. For the effect on variable C, and typically we're going to take these just to 1 decimal point. We can take them all the way up, but significant digits are important. Main effect of variable C, we go do the high and the low. So here, they're kind of all scattered around. And this is why you want to use a software. Imagine if you had to do 16 experiments and you had all of these running all around. It's very easy to put the wrong one where. Now, when I went to college, I didn't have Minitab. I didn't have a fancy calculator. We had to do all these things by hand. It was not fun. So we had all kinds of fancy tables and ways to do these by hand. So we were calculating the high responses again, the 8.5, the 8.0, the 5.7, and the 5.3, adding those up, dividing by 4, getting that average. Doing the second one, getting the lows, 8.2, 7.9, 5.9, 5.4, divide that by 4. So I've got my first high response average, my low response, subtract the 2, and see what I get. So that's all there is to this. You have calculated the main effects of B and C. So let's see what our answers are. So now I've put the answers in here for you. And you can see the 0.43. Some brave soul I saw put their number in the chat. Thank you so much for doing that. You're awesome. And then for the main effect for variable C, it ends up being 0. So the between the shifts, there was nothing. There was no, it's flat. There's nothing there. Let's look at how we put this on a table. This is called an effects and interactions table. Excel does this for you. Minitab does this for you. I have a nice little spreadsheet that came out from the statistics division eons ago. And I still use it today. It's the best little pocket tool I have in terms of it. You just put the numbers in Excel and it gives you everything out. I just love it. But here my effect of the spring A comes in to be at 2.6, and that's my highest absolute effect. So that's the absolute value, if you remember, if it's positives or minuses. And then you rank them in order, which is going to have the most effect to the next, to the next. Now let's see what our graphs look like. So we're not looking at the magnitude of the effect. I'm not graphing the 2 here, or the 0.4 or the 0. I'm not graphing the magnitude of how tall. There are later on, there are some software that do that for you, because it's a little bit easier to pick out which is having the biggest effect. I like looking at the angles to see how big of an impact these things are having. So these are the 3 variables. So now I'm going to give you some really fancy special statistical talk. I have calculated the main effects of my 3 responses for my 3 variables, 2 levels design of experiments. And I have graphed the impacts of those responses. Doesn't that sound fancy? All I did was take a couple of set of numbers, got some averages, and subtracted the 2 averages. That's all I did. And then I made a simple graph, high to low. That was it, low to high. These are just the responses. And that's what this is. Now I can just look across here and I can say, okay, visually speaking, which variable is having the effect, which is having the main effect, which is having the most impact on my little bitty angle. And clearly it's the spring. There might be something going on with the fixture. We'll see if there is an interaction between the fixture and the spring. Find that out. But the point is that it's the spring. And these are in-spec springs. Keep in mind, we're using product that's inside of the specification. And here what I might want to do is I might want to tighten the specification or only pick out, a certain kind of spring. Now, if I'm looking at my interactions for my A and C, so if you remember, A was the spring and C was the shift. And it's the same graph being drawn, but now they're done on the same graph on top of one another. And the math is here for the first example so that you can see how that graph is produced. But they're parallel, they're right on top. Therefore, they are not interacting. The strong interactions are seen where it's, perpendicular, and you've got a big crisscross going on. A and B between the spring and the fixture, the first fixture or the second fixture, completely parallel. And then between the shifts, the C, which is the shifts, and the two fixtures, completely parallel. So in this exercise, none of the three variables are interacting with each other, and it's the spring that's the culprit all by itself. So what the team did was we worked with the spring supplier. We had them, separate the springs a little bit more by the K factor. And by doing that, we were able to eliminate completely all the scrap in that production process, and we were getting the right angles that we needed. So there's lots of combinations out there when we're doing gauge studies. You can have lots of different variables. In this case, this table has 16 variables, or excuse me, this one has 8 variables, and this is 2 levels. So if you're going to do 8 variables at 2 levels, that's 2 to the 8th power. That's 256 experiments. This person, they really decided they needed all 8. There's lots of different kinds of experiment grids out there. Plackett-Berman allows you to do, they figured this out. So I could have done all 256 of them. But after a while, some of these things start to replicate themselves in terms of those pluses and minuses. And then you can eliminate some of those rows statistically. And by doing that, you can really cut down how many experiments are truly needed at the end. All of the software, the statistical software packages will help you do that to minimize how many you really need. JD, I like to keep it simple. I typically do a 2x2 or a 2x3. If I don't see anything right away by using the Pareto, what do they think it really is, these top 2 or 3 items, then I'll iterate it again with another 2 or 3 items and see if I can capture it in the next round, because it's so much faster to run just 8, and then maybe with only 2 replications. But the criticality of running the MSA is what you have to do first. But what we've done is we've walked through an overview of the basics of design of experiments. It is taking an average of a couple of readings, subtracting the 2, and plotting them on a chart and seeing if they have an angle or not. That's all there is to it. If you want to see if there's an interaction, are they crisscrossing each other in the graph? We just learned how in concept this works. So I thank you all for your time. And would like to know if you have any questions, and we'll see what we can do. I'm going to end my show so that I can flip through my deck if there's certain questions that need to be answered. So Doug, if you want to open it up to that, and then we can go from there.
Certainly. I've been capturing some of the stuff up above, some of the questions. In answer to Louise, you want the PowerPoint, email JD. Her email is... let's see, is it on the screen?
No, just join me on Frontier, or excuse me, join me on LinkedIn and ask me for the thing on LinkedIn, and I'll send you the deck.
That'll work.
I'll send you the PowerPoint of the deck, or the PDF, excuse me.
Yeah. So we have several questions. So Claudio, back at 18 after, he said, where did this 1/3 of the times come from in slide 8? Let's go back to that one and see if you can, you said 1/3 of the times.
So here, in my first one, but let's say I got an X, my part rate's 10, but the gauge error is 10%. So the unit could be an 11 or it could be a 9. So if I did, if I rejected this 10, I would be wrong 1/3 of the time, because if I would have three parts that read 10, my chances are one of them is probably a good part, or one of them's a bad part. So that's where it's coming from. It's just the odds of you having a good one versus a bad one, making that right decision because of the error that's inherent in the gauging system. So if you have, I saw someone ask for attribute. Attribute is not using error. Attribute's using agreement analysis, so that's a different percentage. It is a similar kind of process, though. You want to make sure that your people are very able to repeat and get the same answers over and over and over again. Confidence. Oh, say, go ahead, Doug. The things
Oh,
are flying
okay.
through and I can't see
All
them
right.
all.
So Ronnie asks, you said to start with the 2 or 3 variables due to the 80-20 rule. Is this better than to do? Is this better than doing a screening DOE with factorial or half factorial when you remove interactions but still include more variables main effects? Why do you think the 80-20 idea is better?
I mean, it's just common sense. Yeah, you can do if you are dealing with high complexity, let's say making capacitors, and you've got a big flower batch, or you're running a plastics extrusion plastics, and you've got 10 to 15 variables going on simultaneously. In those kinds of cases with a lot of complexity, then that definitely makes a lot more sense. For me, typically in my real life application, and I've done all kinds of processes all over the world, I just ask the guys, what do you think it is? And they say, well, we think it's, A, B, and C, and that's what we go with. Most of the time, they're right. And we get it. We typically figure it out, dial it in within the first 1 or 2 experiments. I haven't had to do too many beyond that. So it's definitely an approach that can be taken uh, with high complex processes.
Okay. Another one here was, what did you mean? You said, and Steve Shulka answered this one. What do you mean that replication helps in the accuracy of the data? Isn't this granted by calibration and your GRR? Steve Shulka answered, replication helps with the analysis of the data. Do you want to add to that?
Oh, Steve's always right. He's my hero. So, I mean, if you just rely on one set of data, one replication of my 8 experiments, if I've got any gauge variation going on at all, my result is going to be super, super sensitive to that. By doing replications, I'm taking the average of these answers, and that's balancing out, it's watering down any effect of a single impact of a single gauge.
Okay, good.
So anytime you can replicate even 2 or 3 times, it gives you a stronger, a more robust set of results.
So I think you're suggesting that rather than do more runs for more variables, it's better to do more replications to give you accuracy.
That does help too, but sometimes you still need more variables. Sometimes you'll need 4 or
Yeah.
5. I mean, I've done my fair share of Plackett-Berman, don't get me wrong, but that to me is a last resort. And Plackett-Berman to me is one of the favorite ways to do a 7 or 8 variables all at once in a very shortened manner.
Okay. Speaking of pre-canned routines, Arthur asks, can we overlay Taguchi to reduce the number of actual experiments we have to run?
Oh yeah, as I showed on the last screen, whatever software you have or using to do your design layouts, you can pick a model that you think will be more reflective of what you want to do. After you get beyond 8 experiments, when you get into the 16, 32, more and more, there are lots of shortcuts that can be taken out there that are statistically valid. And in these, it is helpful then to run 1 or 2 replicates. But here, this is I'm doing 8 variables on this one. And I've got 16 experiments. That's 16 times. This is 32 experiments if I run it twice. But I really do want to do that because I've got 8 variables going on, and I want to make sure the robustness of what I've got. And the MSA is even more critical than ever, because if I'm going to be making assumptions and responding to which one of these things have more effect based on their angles or based on their interaction. So these answers are really, really super, super important.
Okay. We got a lot of really great questions here. One of them said, please comment on confidence intervals 95% versus 99% against sample size. Could you talk about the impact of sample size?
The impact of sample size.
I guess the 95% versus 99% confidence intervals.
I'm gonna ask Steve for that one. This doesn't really, for me, what I'm looking at here is I'm taking the experimental results that I've got here. I've got the impact on them in terms of the gauge error that's in the system, or the attribute agreement analysis, the statistical accuracy that's in here. And what I want to do is, whatever my results are, it's going to be based on how those graphs are looking. But for the more replicates you do, the more effective your answers will be. 99% gives you more confidence versus 95. You're talking about your alpha and beta there. But to me, I'm just looking to see how my measurements are coming out.
Okay. A couple of comments. People would like the recording. You'll get an email in 48 hours, which will have a link to watch the recording by way of WebEx's server. In a week or so, we will get the recording up on the YouTube site for QMD. So you get several ways to find the recording.
Yeah, and Michael gave a good answer too on some of these formats and tools in terms of what tool to use. Also, there's lots of software out there. So Michael just put a link in the chat for the folks.
Yeah. Some of the people are saying that they don't have LinkedIn Premium, and so they tried messaging you and they couldn't. You'll get her email. You'll get JD's email when we send you the email in 48 hours. And if you want
let me do this.
file.
Let me put my email right here for you guys. That way you can do it right here.
That'd be great. But again, you will get an email.
Marhevko at frontier.com.
How to reach her. Okay. Here's another one. Well, yeah, she's typing. So here's another good question. So if there's a strong interaction, how would you approach it? Would both factors be considered at fault and do further investigation?
Ask that again, Doug.
If there's a strong interaction between two different factors, would you want to look at both factors or do some further investigation on it?
You absolutely can, because there can be more than there can be other things affecting those as well. So you might need to do two other variables around those, or you might just want to do a 2x2 to see if there's other effects going on. Once you've isolated a factor that's causing an effect or an interaction, then you can do all kinds of things with it to drill in and to make it better, or to understand it more. You can start to experiment with what range you're going to deal with it. You can cut the range in half. You can do another one with three levels, low, medium, high, to see if you can really optimize how that's affecting. Many Minitab and the other software packages, they have a slider bar where you can say, if my value is this on this item, which one gives me my best set of results. So it's pretty cool. Let me see if I can find. Let me see. Hold on just a second. I want to see if I can find a software. I want to find my documents first. Okay. Let's see. What am I looking for? I am looking for MSA. No, that's not MSA. This is going to be DOE. I'm looking for a DOE tool that I use here. There it is. So this came from the statistical software group, the ASQ statistical software group in the 80s. That's how old this is, but it still works quite nice. And it's got the instructions on how to do it. This is a 3x2, 3 factors. It does a little scatter plot for you.
Are you showing this or not?
Yeah. Oh, I'm sorry. I thought I was sharing. Am I not? I'm in Excel. Sorry. Hold on. I've got to reshare my screen. Bear with me one moment, please.
Okay, that's fine.
Let me get back to the group. How can I get back to the group? Share. Okay. Share content. All right. I'm just going to share my screen. Okay. Let me know when you can see it, Doug.
Got it.
Okay. So this is that experiment done in Excel. I've got my experiments 1 through 8. Here's my springs, the high and the lows. Here's my fixture. Here's my shift. Here's my 3 sets of examples, my results from my replications. And if you guys want this, I suggest you ask the statistics division because Steve is on the call.
Okay.
But I don't know if they have an update to this or not, but this is what I use it all the time. And here what you can use is those little sliders are in here so I can optimize one way or the other by making my settings higher or lower, and then it can help me figure out which way. I'm hesitant to share the spreadsheet. This is from quite a while ago, but I would suggest you use Minitab or some other approved software. It's not hard to do this in Excel, but they do the software. So I would recommend that you guys just use the statistical softwares that are available to you, whichever ones you use.
Okay. So, yeah, so many great questions. So another one here was, so Alexis says, you said to do an MSA first, or the DOE data won't be meaningful. If your gauge R&R suggests your precision is much greater than 10%, do you still proceed with the DOE to identify the variables that are messing up your precision? Or is DOE not the right tool for that?
If you don't have a good measurement system analysis, if you don't have a good gauge R&R of 10% or less, it doesn't matter how you're measuring. No matter what way you do it, it's going to be wrong because your data is not effective. You're not getting a good repeated answer out. And if you're trying to do anything and adjust your process and do a little more or do a little less or a little faster, a little slower, if your result isn't accurate, it doesn't matter what you're trying to change upstream. So you've got to fix whatever's going on with your measurement system first. You may or may not need a DOE, but it doesn't matter how you're going to try and fix your process. If your measurement system isn't effective, you're screwed anyway.
Okay. So, wow. Another one here was, with your value matrix and table, is there any way to eliminate reoccurring value sets automatically, or do you have to do it manually?
Oh, you mean like down in here? So if this is done automatically by the softwares. So whether you're using whatever statistical software you're using, all of those different formats and structures are out there. They're selected automatically. You just pick which one you want based on how many variables you have, how many replications you're going to do, whether you're using 2 levels or 3 levels. You can do a mixture. You can do, I'm going to have 2 levels of this and 3 levels of that and 4 levels of this other thing. I mean, you can make these things hideously complex. I don't recommend it, but people do because they like to.
Yeah.
But yeah, the software automatically sorts that out for you.
Yeah.
All you do is put in your data results and the interactions tables will come out. The actual physical graphs of the different pictures will come right out. And that's, I mean, that's the best way. It'll just pick up all the graphs right away. And you'll see this immediately, and then you can see, it's this, and it's this and that together.
All right, so there's so many good questions, and I think we're kind of running a little short on time. I do want to point everybody to the chat window. Thomas has added a link to QI macros. QI macros is an Excel add-in that is a statistical package. It is way less expensive than Jump or Minitab. Now, what I've noticed though is Jump and Minitab have great help. Okay, there's a whole encyclopedia behind those software packages.
Yeah.
And so if you don't do it very often, having that encyclopedia kind of helps get your head straight.
Yes,
if you do this all the time, well, maybe less expensive software actually works. It's kind of counterintuitive.
Yeah, so one thing I'd ask everybody on the call, if you enjoyed this, if it was helpful to you, put a shout out on LinkedIn. let your community know the value you got from this, so that as we hold more webinars, this helps us add value to our quality community at large.
Okay, so what I guess with that,